All right, guys. So let's now think about distribution of molecular speeds. Um, since we're considering system with a very large number of molecules, as you can think of, right? So we can't expect all of them to move exactly at the same speed. They have different speeds, some moving faster, some moving slower. And let's say if we can calculate some kind of average value, right? Then definitely you can find number of molecules moving faster than average, number of molecules moving slower than average. So what we're going to see here is that James Clerk Maxwell, in about 1860s, um, derived an expression that describes distribution of molecular speeds. Um, and this equation, basically right here in front of you, so this equation is a theoretical value that he actually came up with because Maxwell was a theoretical physicist. So he would come up with an equation using all the given variables, and then experimentalists had to verify that. Sometimes his equations were so brilliant, so ahead of time that it would take a long time for the experimentalists to catch up. And this is one of those examples. I think it took about 50, 60 years for the experiments to show that his equation is indeed true. Because at this time, when he came up with this equation, we didn't even have a true experimental verification that like molecules, or atoms even exist. But in any case, so he came up with this equation, which basically gives you the sort of like distribution of speeds. And this equation shows that this distribution, right, this equation can be plotted, and it's very specific temperature dependent. That means this equation and basically, or this graph, right, is for very specific temperature. If you have a different temperature, the graph shape will be different. Now, one of the things we're going to see here is if we, for example, um, take, a container, like things like this. So let's say, imagine, right, you have some kind of container with n number of molecules. So n is the number of molecules that we have, the total number of molecules. Now, if you want to look at in terms of the speed, right? So let's say what you have here is that which one of them are moving faster, which one of them are moving slower. Then you have to look at the entire system. But we can think of, like, let's say, choosing one sample speed, for example, which would be v plus dv. We can then integrate this over the entire thing and find n number of particles. Now, this graph gives you three things. It gives you the average velocity, approximate position of the average velocity, RMS velocity, but then this graph picks at the most probable velocities. Okay. Now, the idea here is if you take this equation and if you integrate from 0 to infinity f of v dv, this answer should give us n. And I want to do this derivation for you guys so you can see that this is indeed true. So let's look at the derivation here right now. Okay. So again, what we're doing here is imagine, right? So you have a container with certain number of n number of molecules, and we want to look at in terms of how we can use this Maxwell's equation. The idea here is if we take and multiply both sides by dv and then integrate this from 0 to infinity, right? Then this is going to be then give you the entire distribution because the function here is pretty much the area under that graph. Okay, so let's do that. So in terms of then doing this derivation, let's say if I'm doing the integral from 0 to infinity f of v dv, and where f of v here is 4 pi n, then m over 2 pi k. This is a Boltzmann constant t, 3 halves, v squared, then e to the negative 1 half, mv squared over kb, kb times t, and this is dv. All right, so these are not your typical simple, derivatives. integrals. So we're gonna have to look at the one of those tables, integral tables. And one thing we can see here is we can find something that resembles this one, because we have, you can see, right, you have v squared over here, and also v squared in the exponent, right, of e. So this is similar to integral from 0 to infinity x squared e to the negative a x squared. So if you do this, x squared e to the negative a x squared dx, the answers will be square root of pi over 16a cubed. So that will be the answer for that. All right, so let's look at what we have over here. That means, using this, let's say from integral table, we can then integrate our Maxwell's, distribution function. All right, so let's look at what we have. So from 0 to infinity, then if I'm writing the 4 pi n, and I have m over 2 pi kt 3 halves v squared e to the negative 1 half mv squared over kt dv. I can see that from here, my x is equals to square root of mv squared over 2kt, or x squared is equals to mv squared over 2kt, right? So if you're comparing that, so you should be able to see that. So this is basically my x squared. All right, so and then my v squared, rearranging from here, right? I can say that v squared is equals to 2kt over m times x squared. All right, so from which I can also get the dv. So if I say then v is equals to square root of 2kt over m, since x is squared, it can come out of this, so it becomes x. And then if I do the dv dx, so this will be then 2kt over m dx. All right, that means, I have something to replace my x squared, something to replace my v squared, and something to replace my dv. So when I go back to my equation, now I can plug in the, or replace the, v squared and dv with the other, derived, let's say, expressions. All right, so then I have 4 pi n, and then I have m squared, sorry, m over 2 pi kt 3 half, okay. And then I have a v squared. Well, my v squared is this one over here, which is 2kt over m times x squared. Then I have e to the negative 1 half and what I have here is basically I have mv squared over kt, and I can see, right, that mv squared over kt here is just x squared, so it becomes x squared. Sorry, that 1 half is actually part of that, so just x squared because it's 1 half is right there. All right, and then at the end I have dv, where dv here is equal to that, which is square root of 2kt over m dx. All right, so I got this once I replaced all of my quantities. That means v and a dv I replaced in terms of then x, right? Then I can go from here and factor out all the the constants and things like that, and move them out of the integral if I want to. So Here's a constant, here's a constant, here's a constant, here's a constant, right? All of those are basically constants. So I can remove them, 4 pi n. Then I have m over 2 pi kt, 3 halves, and then 2 kt over m, and then square root of 2 kt over m. So those are my constants. And then from 0 to infinity, x squared e to the negative x squared dx. All right, so I got with that. All right, so now what I can see from here is that this term is m over 2 pi kt to the three halves, and those two combined together, so 4 pi n, so then m over 2 pi kt 3 half, those two combined together then will give me m 2 pi sorry, just 2 kt over m 3 halves. Okay, that means if I do, this is to the 1, this is to the 1 half. If I'm multiplying them, I can just end up adding them together. 1 plus 1 half gives you 3 halves. Okay, so and then this integral over here basically going to give me, just like you can see from the top, right, when we had the the function over here. Remember, so this has to be equals to square root of pi over 16a cubed, but for us a is equals to 1, so it becomes pi over square root of pi over 16. Okay, that's what integrating that will give us, pi over square root of 16, which is basically square root of pi over 4. Okay, but now those two together, since here I can cancel the m's and 2 kt's, that means what I have here is this 4 pi n, then this becomes 1 over pi 3 halves, because the pi is the only quantity that does not end up canceling out. And then this is equals to, sorry, not equals to, this is basically times, because this is times. So then it's times square root of, a pi over 4. Now, since I have 1 pi over there, and I have the square root of pi over here, that together gives me then pi 3 halves, cancel that, 3 half, this 4 cancel with that 4, that means pi over, pi 3 halves and 1 over pi 3 halves, they will cancel, and the only thing then end up surviving is then this n, and that will be then our final answer. That means integrating this whole thing, right, will give us final answer as n, which is the total number of molecules. All right, so let's go back to the here. So that's why if you do the integral, right, you're going to get total number of molecules. All right, so we can see, right, also that this distribution, as I mentioned, is temperature dependent. That means every temperature going to have its own graph, or in terms of different shape, and that will be in terms of, let's say, remember we talked about that temperature represents the overall, like let's say the average kinetic energy of the particles, and the faster they're moving, right, indication of a higher temperature. And this is kind of like what we have in terms of the distribution of two different temperatures, right? You can see, right, higher the temperature, different the shape. And also one of the things we have here is that yellow and orange, part of the graph represent the particles moving at the speed faster than, let's say, most of the other particles. And generally that represents, when they have enough energy when they collide with one another, so they can actually partially penetrate each other. And the energy that required for that to happen is called an activation energy. Okay, and activation energy also dependent on specific type of like chemical reactions and things like that. So that's why generally what we have here is, you know, let's say when the temperature, you know, is high, usually what you get here is, you know, many chemical reactions, right? The, you know, things like this happen much more rapidly because of the higher temperature coming with the higher number of particles moving at the higher speed, and much higher number of particles actually having this activation energy. All right, so let's look at another example over here. So use calculus to show that f of v given by equation 18.6 has its maximum value at the speed v max equals 2 kt over m. That means this is basically we are looking at in terms of which one, or like let's say taking that equation, right, Maxwell's equation, and showing that at the highest, you know, the highest speed that they have is equal to the square root of 2kt over m. Right. So we take then the function that we had. So this was 2 pi n m over 2 pi kt 3 halves, then v square e to the negative 1 half mv square over kt. All right, so we take that and then take a derivative of this with respect to, you know, with respect to v. So df dv. Okay. So this will then give us so if we do the integral, you can see, right? So pretty much what we have here is we have v over here and v over there. So to do the derivative here, we have to use the product rule. Okay. So to use the product rule, then we can say, all right, so 2 pi n m over 2 pi kt 3 halves. So this is basically pretty much a constant, right? I don't have to worry about. But then what I have here is this. It's dv of v square e to the negative 1 half mv square over kt. Okay. So that means in terms of then what I have to do here is, if you remember, right, if you take in the derivative, if you have f of x, let's say g of x, and then you take in the derivative of that one. So you then do g of x derivative of f of x dx plus then f of x, then derivative of g of x dx. So using that, then we can say that, you know, this derivative, right, derivative of f of v dv is equals to, so again, 2 pi n m over 2 pi kt 3 halves. Then if I'm taking the derivative of this one, that means I take the derivative of the first term, which is v squared. That just gives me 2v. Then that means now I treat the second term as a constant, so it becomes e to the negative 1 half mv squared over kt. Okay. Then plus, then treat the v squared as a constant, and then take the derivative of the second term, which is e to the negative 1 half mv squared over kt. So then this will give me, so e to the negative 1 half mv squared over kt. Get rid of that so I have enough space. And then take the derivative of the, you know, the argument of e, right? So which is, you know, negative 1/2 mv square over kt. So this will give me negative 1/2 2v over kt. This. All right, there you go. So from here, this 2 can cancel out. And what I have here is 2 pi n m over 2 pi kt, 3 halves. Then I have 2v e to the negative 1/2 mv square over kt. Then this minus goes in front, so minus. So I have v square here and v over there, so it becomes v cubed. I think I forgot to put m over there. So mv cubed divided by kt, then e to the negative 1/2 mv square over kt. Okay. Now, then I can say this is equals to, finally, I can actually factor out those, e to the negative 1/2 mv square over kt because both terms have it. So 2 pi n over m over 2 pi kt, 3 halves. Then here I have 2v minus mv cubed over kt, and then e to the negative 1/2 mv square over kt. All right, so that's basically the expression. So that's taking the derivative. Now, to get then the maximum value, that would be when this derivative, the f dt, sorry, dv, is equals to 0. Okay. Well, I can see that from what I have here is the only way that I can get 0 if this, this is 0, right? Because everything else pretty much a constant. So if that difference here is 0, that means 2v minus mv cubed over kt is equals to 0. And then from here, I can say that mv cubed over kt is equals to 2v. And I can cancel that and then solve for the v, where v is equals to, and obviously this has become like, let's say then v max, right? So since I'm using this condition, then I'm looking at basically v max. So v max is equals to then square root of k 2 kt over m. Okay. So that will be then my final answer for this, for this example, which obviously verifies this, that the maximum value is indeed square root of 2 kt over m. All right. Now, if you proceed, then looking at some of the real gases compared to the ideal gases, we will see that there are some differences definitely when we consider the real life, let's say, situations. Because again, some of the ideal gas, this concept, right? We ignore some of the, some of the things, right? We make some assumptions, and let's say we ignore other type of energies, like potential energy between the particles, all the other type of interaction that they can have. And remember, we only considered the type of interaction that is coming from the, let's say, container wall, and the collisions are perfectly elastic and all of those things. Well, obviously, there are a lot more variables involved than, let's say, we did in deriving the ideal gas equation. And this graph pretty much demonstrates that if you are looking at a curve for the real gas compared to the ideal gas, we will see then there are some differences in a way that, for example, in this diagram, that you can see that dashed line, right? This A prime and B prime are the examples of the ideal gas law. Okay, but the solid lines represents the behavior of the real gases, and we can see, right, already, going from, A to B to C to D, there are, pretty much a major differences. So for example, the curve A actually represents higher temperature. So if you're looking at this diagram, this is a PV diagram, pressure versus volume. These PV diagrams give you how the, let's say pressure increases here up, volume increases here to the right, but also temperature increases like that. So that's another information that we get from here. That means temperature of the curve A is greater than temperature of curve B. Temperature, curve C is less even, and D is even less. That means temperature of the curve D is the lowest from that bunch. And that means, closer you are to the origin, lower the temperature. And we're going to talk about this, these are known as isotherms. So for a diagram like this, we can think of like temperature basically goes like this. So those are the lines for the same temperature. So that means, the first line, everywhere temperature is the same. Second line, everywhere temperature is the same, but higher than the curve one. Third one, all the temperatures the same along the curve, but higher temperature than the curve two, and so on and so forth. That means that's how the temperature, those isotherms, can be used in a diagram, PV diagram, right? So basically, you're getting a two-dimensional graph, but getting like three-dimensional information. All right, so from here, we can see that when you go from A prime to A or B prime to B, you do get discrepancy in terms of that the graphs don't behave, right? They don't follow the same curve. Well, that's because when we talk about, let's say, the higher pressure, right? Um, Remember, we expect molecules to be closer together. We expected that we ignore any type of other energies like potential energy and things like that, or any type of attractive forces like that they can have between them, and that can be used to explain why there are some discrepancies. And when you go at the let's say, especially right at the higher pressure, right, you can see there are discrepancies in terms of that. Another thing we can think of is that when the pressure decreases, right, so at some point you and the temperature decreases, for example, for the curve B, C, and D, right? So as the temperature decreases at some point, then you can have what we call changing phase, when you can have the gas go from a from solid the gas phase to a liquid phase. So it can have a liquefaction. So in terms of here, then you can take a, like, let's say when you're considering curve D, for example, so you have at point D, right, when you start at a low pressure, which is, let's say, somewhere over here. So what you have here is that you're looking at the substance, right, as in the form of gas. So it occupies a large volume. But as the pressure decreases, and you can see, right, already this D is at the lowest temperature. So, but as the pressure increases, so the volume decreases, and it's more or less initially following the type of, let's say, curve that we would expect. But then at point B over here, okay, so at point B, the volume decreases. At this point, you can see, right, we get a vapor. So you can see, right, we get a vapor. So at this, from that point, there is no change in volume, right? No change in volume, because it is going from liquid, it's entering this liquid vapor region. Okay, that means entering the liquid vapor region, and all the way until it reaches point A. Okay, where then from point A you can take, like, let's say now we have it's in a liquid form. Okay, again, so when we go from B to A, um, you can see, right, the graph represents basically very little change in pressure. So there's really very little change in pressure from B to A, and then from A, then you can say that whatever the system, the substance that we have completely changed to liquid. Okay. Then from here, as you further increase, the pressure, you can see that the volume increase is minimal, and that's because when you're liquid, right, liquids are pretty much incompressible, so it's harder to compress or change the volume of the liquid compared to the gases, right, when it's in the gas form. All right, so then this is also the region where you can have the substance to be both in vapor, which is gas, and liquid, phases. They can actually uh, be at this, like let's say what we call in equilibrium. So that means they can exist together, while in more or less you can think of, like let's say they are in this particular region, because before B it all was gas, after A it's all liquid, from B to A, then slowly all that gas is then condenses into a liquid until eventually you have a liquid. If we look at then curve C, that basically represents a behavior of a substance where this point C is considered to be a critical point. Okay, so that means it's a substance at the critical point or critical temperature. Okay, because what we have is that at the temperature is less than the critical temperature, okay, the gas will change to liquid phase if sufficient pressure is applied. Okay, above the critical temperature, you can see, right? So, if you right here, okay, if you have a little more pressures, you then can go and become a liquid phase. Above that critical temperature, no amount of pressure can cause a gas to change phase. Okay, that means if you're here, right, for example, if you're over there, that pretty much will not happen. Okay. So and there are tables here with a table here with a value the critical temperature and the critical pressure for different substances, like for example for water, that happens at 374 degrees Celsius or 647 Kelvin, and critical pressure in ATM is 218, and so on and so forth. That means we have all of those in terms of like different substances that we can have. Okay, so in a way, this table gives you the most commonly used substances that you might need for the, let's say, homework assignments and things like that. So always refer to this table if you need to get those values. All right. So one of the things that we also have here is, instead of doing the pressure versus volume, right, PV diagram, we can also do a PT diagram, which is pressure versus temperature. So the PT diagram is also known as a phase diagram. Okay, so it tells you, you can see, right, it gives you basically three regions. Okay, so and the lines, those red lines, represent the equilibrium lines. So that means, this, for example, this line over here, SV, where S is for a solid, V for the vapor, gives you under which condition in terms of temperature and pressure you can have a substance going from solid to a gas directly. At this point, right, you have a triple point where all three phases can coexist together, and then you have a LV where basically this represents the curve going from liquid to a vapor. This one solid to liquid, and then what you have here is that you have then basically that, remember the critical point, right? The temperature when the liquid goes to a gas. When you apply a little bit more, let's say, pressure. At this point, you can see that those regions, right, solid, liquid, and gas, follow kind of like what we know already. Because, for example, when the pressure is 1 atm, 1 atmospheric pressure, and let's say this is water, right? We know that water changes phase from solid to liquid at exactly 0 degrees Celsius. Okay, that means at 0 degrees Celsius, in order for a solid to become liquid, you need to have a 1 atm. Well, obviously, you can see, right, if your pressure is, for example, 0.006 atm at 0 degree temperature, right, it doesn't happen. You need to increase your temperature to 0.01 so that you can actually go, and melt, let's say, the ice. So then that means this graph, right, this phase diagram tells you, those are the conditions, right, going from a liquid, solid to liquid. These are the conditions, for the liquid to, let's say, gas. And you can see, right, it's a pressure and temperature, right? So if you talk about, let's say, atmospheric pressure, draw this line and see what you have for the melting and then for the boiling. Okay, but if you have a different pressure, then things change. At some, uh, uh, you know, you can see, right, at some pressure, when the, let's say you have a low enough pressure, the you can go from a solid to a vapor without even going from, into a liquid phase, right? So you can go from a solid to a vapor directly. All right. So this is known as a sublimation. So the sublimation is when you go from solid to a gas directly. All right. So we have the melting point right here, for example, right? So that means if you're at 1 atm, you'll never have a sublimation, right? So if your pressure is 1 atm, you're going to go from solid to liquid and then from liquid to a gas. Okay. But if your pressure is very low, then you can actually do have a sublimation. So that means the condition have to be, appropriate for that to happen. Okay. So this particular diagram is for water. Okay. So one of the things we have here is for water, the diagram will be a little bit different compared to anything else. For example, this is carbon dioxide. So most of the things pretty much the same. So you have a region where there is a, SV region, right? And you have a LV region and you have a SL region. And what you have here is, for example, you can see, right, the pressure, the temperatures are all different for the carbon dioxide. So let's say the triple point, happens at 5.11 atm and negative 56.6 degree Celsius, right? And then we go, let's say it's 56 atm, then you can say that it goes from a solid to a liquid. And let's say, for example, you can see, right, that the, room temperature, um, you can have this, basically going from a liquid to a vapor. Okay. And critical point is happened roughly about 31 degrees Celsius, and when you have a 73 atm pressure. Now, also look at then in terms of what we have here for the curve for the SL portion, and that curve looks a little bit different, right, compared to the water. Okay, so the the shape is different for the water because remember the water is different in a way that when it freezes, it actually expands, right, the volume compared to the pretty much everything else. So that's kind of like what we have in terms of the water, that you know substance expand upon freezing because uh, solid ice actually expand more, right, compared to the liquid ice. So that means if you lower the temperature, you expect sort of like, let's say, water. Remember we talked about that, right? Water behaves a little bit differently compared to the other substances. Okay. All right, so let's look at then this example over here. It says the phase diagram below can be interpreted to yield information on how the boiling and melting points of water change with altitude. Okay. Explain how this information can be obtained and how might this information affect cooking procedures in mountains. Okay. So now one thing we know here is, let's say if this is Earth, so our pressure is highest at the ground level, right? And as we go, with altitude, pressure decreases. Okay, so pressure decreases with altitude. Okay, that means one thing we can see here is, for example, this we have, like, let's say O is the triple point, right? Let's say here we have a point C. So let's say what we have here is this is OC over here, thing like this. So here the high pressure, here's the lower pressure, more or less. So P high, P low. So as the as you increase your altitude, P decreases. That means, in a way, increasing in altitude. Okay. So our graph basically shows something like that, downward, information, right? That means, this you can think of like, let's say this represents something like a ground level, and somewhere over here represents then the mountain. Because as you increase with altitude, your pressure decreases. That means the temperature at which, for example, the water is boiling will be decreased if you're on top of a mountain, right? I mean, this is obviously, I'm going to sort of like a dramatic, effect, but that's kind of what we have. That means the temperature of the liquid gas interface, which is this one, right? LV interface, decreases as the pressure decreases. So the boiling temperature decreases. Okay. So as the boiling temperature decreases, that means the water will be boiling at the lower temperature on top of the mountain compared to the, at the sea level. Same way, if you're talking about this graph over here, right, for the OB, which is basically represents the, SL. So then the melting temperature increases with increasing altitude. Okay. So again, you know, this is lower altitude and this is higher altitude. You can see, right, going from low altitude to high altitude, you are increasing your temperature. Again, how do we know this is a low altitude? Well, because pressure is higher at the low altitude, and this is the um, high altitude because pressure is lower at high altitude. And you can see, right, that the graph shows that there's a increase in temperature where for the melting, but decrease in temperature for the boiling. Okay. So part B says, how might this information affect cooking procedure in the mountain? Well, it's going to take a longer time. So boiling at the lower temperature means that the cooking time will have to be increased. Okay. Because there's amount of, like, let's say, energy that you do, right? Because when it starts boiling, so amount of energy it is, let's say, absorbing is at a different rate. So it's actually going to take a longer time for it to, give you the same pretty much effect. Okay. Here's one more example. Oh, sorry. Okay. Um, Here's the example. It says, explain why the carbon dioxide on Mars is found in a solid state in polar regions, even though the atmospheric pressure at the surface of Mars is only about 1% of the atmospheric pressure at the surface of Earth. Okay, so what we have here is that the pressures below 5.1 atm, if you remember, right? So what we have here is that the the carbon dioxide. Um, so from here, if you can see, at 5.1 atm, okay, it only it can exist only as a solid or gas. Okay, so that means this is a triple point. So below this triple point, then what we have here is, you can see, right, any pressure below this then goes from a solid to a gas directly. Okay, that means it can, like, sublimate from solid to a gas. Now Mars on average is warm enough so that the atmosphere is mostly gaseous carbon dioxide. Mars polar caps must be cold enough to enable solid carbon dioxide to exist. Okay, that means, we have to talk about in terms of the cold enough. So for that, you have a solid, dry ice, right? So that basic solid carbon dioxide is what we call dry ice for it to exist. All right.